I will speak in English and in português, yeah?
Okay.
Então, bom dia a todos. Bem-vindo à palestra de hoje, que é do professor Narayanaswamy Balakrishnan, da Universidade de McMaster, no Ontário, do Canadá. E ele é professor, Distinguished University Professor, né? Professor de universidade distinguido, é o título do senhor Balakrishnan. Eu acredito que a maioria conhece o currículo extenso do professor, que teve várias honras na sua carreira. É membro da Associação Estatística dos Estados Unidos, americana, né? Do Instituto Internacional de Estatística Matemática, da Sociedade Estatística do Canadá. Então, eu vou agora traduzir para o inglês o que eu falei, né, da minha apresentação do professor Balakrishnan. Então, good morning to everybody. I have the honor to present today Professor Narayanaswamy Balakrishnan, a distinguished university professor of McMaster University of Ontario, Canada. And he has a long curriculum. I think most of you know the curriculum, so I just talked about some honors. Professor Balakrishnan will today talk about accelerated live testing of one-shot devices, data collection and analysis. And without much further ado, I will ask, please, Professor Balakrishnan to start his presentation. Thank you very much.
Thank you very much, Alexander and Jeremiah. Thank you, first of all, for inviting. Jeremiah wrote to me several months ago. I had even forgotten until he reminded me a couple of weeks ago. I'm going to talk about this topic. I don't think I have given a talk on this topic in Brazil. That's one reason I chose this topic. The other reason I chose this topic is also, you see the date there, 28 July 2020. This was during the pandemic. I published a book subsequently by John Wiley and Sons with the same title. So I'm going to talk about this, and a lot of the details that I'm going to give can be found in the textbook. Now, I want to take a few minutes to explain how this problem came about. In 2009 or 2008, I was driving my car on the highway, and I was going at 90 kilometers an hour. The speed limit was 80 kilometers an hour. And all of a sudden, a young lady just came in front of me without any warning. I tried to avoid hitting her, but I could not avoid because the speed and the distance I had, I could not stop. So we had a head-on collision, and she had a Toyota Corolla and I had a Volvo. And after the accident, I noticed that she got seriously hurt because her airbags did not function. And in my car, the Volvo, I had a passenger side airbag, driver's airbag, side airbags, all of them got deployed. I could get out without a scratch in my body, but in her case, she got seriously hurt. I pulled her out and called the ambulance, and then the police came and the two of us were taken to the hospital for a checkup. And she got charged for negligent driving. She was a young lady, like my daughter's age, 18 or 19 years old. While I was coming back from the hospital to home by the ambulance, I was thinking to myself, how would one evaluate the reliability of airbags? For example, You have a car, it may be a Honda, it may be a Toyota, it may be a Fiat, whatever it is. It has airbags. How do you know the reliability of airbags? How does one collect information about this? And at that time, I had a PhD student by name Mano Ling who had just joined. And so he wrote to me that I want to meet with you to decide on a topic. So I wrote to him very excited, saying that I have thought of a problem when I was in the ambulance. I think we should meet next week. I will explain to you the problem when we can work on it. And that turned out to be the start of this topic. So from 2009 on, I have published more than 30 or 40 papers on one-shot devices. And that is what the book is about. And I am going to go to full screen and go over what I am going to talk about in detail. By the way, both Jeremias and Alexander, you tell me when I should stop so I can stop. I don't have to complete the whole talk. It's a long presentation, but you tell me when you are all tired and you want me to stop talking, I can close the session. So this is the text. This is the research monograph I told you about. Accelerated life testing of one-shot devices. And if you see here, this is a car inside picture. And this is exactly what it was in this lady's car. It was a Toyota Corolla. And you see that the passenger side airbag successfully deployed in collision, but the driver's seat airbag did not deploy. So that's a failure. This is a success. And of course, how do you evaluate information on the reliability of airbags? That is the question. And these are my co-authors. Both of them are my PhD students, former PhD students. Now they are professors. So, Hon Yu So is now at University of Waterloo. Mano Ling is at the University of Hong Kong. So here is an outline. And you can see that I have a long laundry list of things that I want to talk about, because there are many different angles that you can focus on. The idea is it is like a short course. Once you go through this lecture, you will find what are all the things that are done. Then you can think about further problems or some modifications to it. So first, I'm going to start with what is a one-shot device. Whenever I talk to people, they don't know what a one-shot device is. One-shot device is a device that gets destroyed during usual operating conditions, and they can perform their intended function only once. Like, for example, airbags. Once you have a crash, the airbag opens and it protects you. After that, the airbag cannot be reused. It has to be removed. A new airbag has to be installed. And in this case, what is interesting is that you will never observe a lifetime. This is even though it is a lifetime data analysis, you will never observe a lifetime data. You will never observe the actual lifetime. All you will observe is whether the airbag was a success or a failure. Like in the picture that I showed, there were two airbags. All in this crash, all I notice is one airbag succeeded, another airbag failed. That's all I know. So examples, it is not only airbags. It turns out that many devices that are commonly used are one-shot devices. For example, electro-explosive devices. In mining, you use electro-explosives, dynamite, for example, and you ignite them. Sometimes the electro-explosives don't function. They are failure. You have fire extinguishers at home. You have munitions. You have rockets, vehicle airbags, devices under destructive life test. Any destructive life test that you do, the item gets destroyed as soon as it is operated. and in which case you always get only a success or a failure. But the problem with it is that most of these one-shot devices may be highly reliable. So therefore, you cannot observe many failure under normal operating conditions. So for example, in car airbags, if you crash at 10 kilometers an hour, 20 kilometers an hour, the airbags won't explode. They won't succeed because the stress was not sufficient. So what you do in order to evaluate the reliability of such one-shot devices, you use an accelerated life testing. What is an accelerated life test? It is meant for capturing valuable lifetime information in a short experimental time. It is meant to induce more failure. And you do that by using higher than normal stress level to induce early failures. So if, for example, I run the car at 50 kilometers an hour and crash into a tree, that is an accelerated life test. At normal speed that they would test it at would be 20 or 30 kilometers an hour. But there may not be many failures in this case or successes in this case. So you use higher than normal stress levels, and then what you do is you extrapolate. You extrapolate from the data you obtained at elevated stress levels to talk about the estimation of the reliability under normal operating conditions. And this is usually done by a link function. And there are many reliability link functions. Need not be log linear link functions or logistic link function. For example, there is something called power law model, Arrhenius model, etc. These are all thermodynamic principles that are used to link the stress factor to the lifetime data. So I'm going to start with a bunch of data, and I want to show you that these are real life data that are just one-shot devices. The first data, it is a data on electro-explosive devices under sea salt. What is sea salt? Sea salt means constant stress accelerated life test. So for example, if the normal speed at which they want to evaluate the functioning of the car airbag is 30 kilometers an hour, you fix 50 kilometers an hour and it's a constant stress. And it is accelerated because you are using a higher than normal speed. And in this particular case, this is a electro-explosive devices, and they use temperature in kips as the stress factor. So I have here 9 test groups, and I have here the temperature, 308 kips, 318 kips, 328 kips, etc. Number of samples that were tested under each test group, and the number of failures. And here the inspection time. The inspection time says, when do you declare a failure? For example, inspection time is important in an airbag. Suppose the car accident occurs. What you want to do is declare a success or a failure within 5 seconds after the accident. The car airbag should function within 5 seconds. There is nothing to be gained if it functions after 30 seconds, because by that time, the driver may have been injured or the passengers may have been injured. So the inspection time is the time at which they test whether the unit succeeded or failed. Here is a second data. This is originally due to Marvin Zelen. It was published in 1959. It is a failure records on glass capacitors. Here again, it is a constant stress accelerated life test. You will see repeatedly this phrase and another one called S salt, sea salt and S salt. Sea salt means it's a constant stress. S salt means it's a step stress. So that means that it is increased, the stress is increased in steps, and the test is collecting data at different stress levels. In this example, I have two stress factors. In the previous one, I had only one stress factor, temperature. And here, I have the temperature and the voltage. So the inspection time again is given here, and the number of samples tested, the number of failures. But notice here, the lifetime data is not observed. It can also arise in biology. This is a tumorigenicity experiment. This is a data that was given by Codell and Nelson in a paper in Biometrics. A tumorigenicity experiment is they have a lab mice, number of mice, and they inject them with a dosage, and the dosage of the chemical that they use is in per parts per million. So for example, I have 24 test groups here, and the dosage, some of them, first 5, they injected with 60 parts per million. The next 13 were injected with 120, 200, and 400 parts per million. Then the number of mice that were sacrificed. So that means after 48 months, 9.33 months, that's the inspection time. After 9.33 months, that is, for example, 280 days. After 280 days, 48 mice were sacrificed, which were injected with 60 parts per million dosage. One of them died with tumor, and the remaining 47 did not have tumor. So what you may want to do here is, once again, use one-shot device testing data. Here is a data from grease-based magnetorheological fluid test, but this is under a S-SALT. S-SALT means step stress accelerated life test. And I want to explain what that is. The stress factor here is a temperature. But you see here, stage 1 was, the units were tested at 333 kips as a temperature, but stage 2 was 339, stage 3 was 345. So there were 4 stages. At each stage, the temperature was increased by 6 kips. The number of samples that were tested are all the same, number of failures observed, and the inspection time for the grease-based fluid is measured. There is another data. This data is called ED01 experimental data. You can find it in a Google search. And here, the number of mice sacrificed, died without tumor, died with tumor, from the ED01 experimental data. And I have given once again the inspection time in months. This is a high dose of 2-AAF treatment, that or chemical that was injected. Some were nominal, that group, which means they were not injected with the chemical. Some were injected with the chemical. So you can ask, has the chemical has the propensity to generate more tumors? The number of mice that were sacrificed, then you ask how many of them died without tumor, how many of them died with tumor. So you may be able to think of them as using the tumorigenicity, whether you want to know whether the incidence of tumor increases with the dosage and as compared to the nominal level. This is a famous data, Berlin et al. Data. It's a survival data. It's a serial sacrifice data on the presence or absence of 2 disease categories. There is one called thymic lymphoma. The other one is all other diseases combined. And there are 14 test groups. These are the sacrifice days. And you also want to know whether the covariate was gamma radiation, where they injected, where they exposed to gamma radiation, yes or no. There were 2 groups. Number of mice, and you sacrifice them. You ask, healthy mice were 58, died with thymic lymphoma alone, died due to all other diseases, and died due to thymic lymphoma and some other related cause. This is a case of one-shot device with competing risks. So towards the end of the talk, if time permits, I will talk about this particular problem, where you can think of competing risk model for one-shot device. So those are the real life data that I will keep bringing in order to show you how the results look like. So now I'm going to start with the inferential methods. What is a typical form of one-shot device data under a constant stress accelerated life test? I think of multiple accelerating factors. For example, I have stress levels here. I assume there are J stress factors. The first group, the J stress factors are at different levels, X11, X12, X1J. I inspect them at time tau 1, and number of devices I test is K1, out of which number of failures is N1. And I have I testing conditions, J stress factors and J stress levels, I inspection times, I numbers of tested devices, I numbers of failures that I have observed. So clearly, the likelihood function is going to take the typical binomial form. Either the devices failed or the devices did not fail. So I will have a typical binomial form where I put the observed likelihood function is if the airbag did not function. So that means the device was left censored. So that means the lifetime must have been smaller than the inspection time. So at the inspection time or test time tau I should have the lifetime to be smaller than tau I, and ni of them failed, so that will be f to the power ni. The remaining ki minus ni function, the airbags exploded, they function, so therefore their lifetime must be after the inspection time, which is the reliability function. So Z is the given data. What are the data? I need the inspection times tau I need Ki, the number of units that were tested, and I need Ni, the number of units that fail. Xi are the covariates, and it is a constant stress accelerated life test. And the reliability function is R, which is a survival function. That is the reliability at inspection time tau I. Now notice, this is an extreme case of censored data. All the data are censored. Either they are left censored, in which case you have capital F, or they are right censored, in which case you have capital R. If the airbag failed, I know the lifetime was smaller than the inspection time. If the airbag succeeded, then I know the lifetime is larger than tau I. So how does the EM algorithm, this is a typical case of EM algorithm. In fact, it is extremely useful because the whole data is censored. So the E step will ask, how I have to impute the missing data, and I need expectations. It is clear that the expectations are not all going to be simple, because when I take the log of this, I will have the left truncated distribution, the right truncated distribution. So I need to work with expectations on both. And the M step will ask that with the imputed values, replacing the missing data, I will maximize. And of course, the reliability engineers commonly work with 4 lifetime models. They are exponential, gamma, Weibull, and log normal. You bring any other distribution to a reliability engineer, they are not happy. Hello? Is there a question?
No. I don't think so, no.
Okay, thank you. So, and then that is EM algorithm can be implemented. By the way, in the book, there is a separate section for each model. And also in the book, the novel feature of it is we have provided the R code and how the R code can be implemented and what kind of results you get, how you interpret them. So, of course, once we have the point estimation, we can construct a confidence interval, but normally we teach in statistical inference course the students to use asymptotic normality of the MLEs. Here, We have the asymptotic normality we can establish using Lipschitz conditions, but the asymptotic confidence intervals may not be reliable, partly because the reliability experiments do not involve thousands of units for testing. Small number of units are tested. So there are a couple of things you can do. Rather than pivoting the parameter phi by using the MLE phi hat and then using the asymptotic normality, since we are dealing with lifetime data, we want confidence interval for reliability function. So if somebody wants to know, I have bought a 4-year-old car, a Toyota Corolla, and this has not been in an accident at all. So I want to know what is its reliability from 1 year from now. So that means you want to look at the reliability at the age of 5 years old, R of 5. So that is the function that you want to evaluate. And in which case we know the R of t is always between 0 and 1. So rather than using the MLE directly, you can use a logit transformation, construct a confidence interval for the logit function of R of t, and then invert it. The advantage of this is that this confidence interval will always be in the interval 0 to 1, whereas this confidence interval is not bound in the interval 0 to 1. Same thing you can do with other things, quantiles, mean lifetime. If I want to know what is the mean lifetime, instead of using this method, I can use the log transformation of mean, which will be from minus infinity to plus infinity, use the delta method to get the confidence interval and invert it, and that confidence interval will always be in the interval 0 to 1, not 0 to infinity. Not only it keeps the intervals, it also has better features. Coverage probabilities are better because these logit transformation and log transformations avoid skewness in the pivotal quantities. And that is an advantage for these methods. So here I give you a small simulation study. I took an exponential lifetime distribution. I have two accelerated life conditions, 25 degrees and 35 degrees Celsius. And I am interested in estimating the mean lifetime, theta e, means mean lifetime under exponential distribution. The model parameter can include everything. Whatever I have used, the link functions, it can include all the parameters. The mean lifetime mu e, the reliability under normal operating conditions of 25 and 35, I have given different sample sizes, k. Remember, k is the sample size here. And I have given here the bias and the root mean square error. Why I have three parameters? Remember that I have a link function because I have two stress factors, one corresponding to 20, another one corresponding to 25. I have 25 and 35 as the normal, but I tested the data at 25 and 30, and I want to extrapolate. So I use mean lifetime theta e is a positive quantity. So I use a log linear link function. It has an intercept. It has a slope for the first covariate, slope for the second covariate. And I have given here the true values. The true value of the mean lifetime is 66.686 days. The reliability at mission time 10 years is 0.799. The reliability at 20 is 0.638. You can see that the bias is all very close to 0, and it tells you that the estimates are almost unbiased, even in the case of small sample sizes. Now, I give you the coverage probability, and this gives you a whole different picture. I use the same setting as before, and now I am looking at the 95% confidence intervals for the model parameter, the mean lifetime, and the reliability function. You notice here that the coverage probability based on the asymptotic method is quite low compared to 90%. It is only 89%. But the same data with the same sample size k, if I use the log link or the logit link in order to change the pivot for the construction of confidence interval, they can attain the nominal confidence level of 95% even in small sample size of 10. This is why I was telling statisticians usually use the asymptotic theory for MLEs, but depending on the quantity you want to construct the confidence interval for, a cleverer approach will be to use some kind of transformation. Some of these transformations, like a logit transformation, log linear transformation, etc., can eliminate skewness in the pivots distribution in small sample sizes and can give you better coverage probabilities, even in small sample sizes. Now I take the electro-explosive device data that was given in this paper in 2009, Fan et al. And now, which distribution should I use? Because you have no data. So you cannot use a goodness of fit to say that I have a gamma or a Weibull distribution, because there is no way to model validate. So model validation is out the window because you have no lifetime data. Complete data is censored. So here I demonstrate, I assume the gamma distribution, I assume the Weibull distribution. The electro-explosive device data, I have 2 parameters for a gamma and 2 parameters for a Weibull. So they have the same number of parameters. Since the shape and scale parameters are both positive, I use a log linear link function for both of them. So there will be an intercept and slope for the scale parameter, intercept and slope for the shape parameter. I estimate the mean lifetime under gamma, the reliability function at nominal time at 20. So this is the reliability function that I want to estimate. Notice that the data was very small, of size 9. So the reliability estimate turns out to be 69.6%, but the asymptotic confidence interval gives you a confidence interval from 0.3 to beyond 1. But we have to truncate it at 1 because it's a reliability function. But if you use the logit transformation, you get a confidence interval always within the interval 0 to 1. You should not worry why this confidence interval is so wide. That is because we have only a data based on 9 units that are being tested. So, of course, if we have a larger data, our inference will be more precise. We can put a Bayesian framework. The Bayesian framework has a problem here. The problem is, how do I specify the prior? That's a question. For example, if I am interested in estimating, this is something that someone like Josemar will have very good idea about. For example, if I work with log linear link function here, I have 4 parameters. Typically, you go to Bayesian inference, what they will do, if I am not mistaken, is say that there is an intercept and slope for the scale parameter, intercept and slope for the shape parameter. So I have 4 parameters. Let us put a 4-dimensional multivariate normal distribution with some mean vector that comes from a priori information. Then you put a variance covariance matrix, which is often taken to be diagonal, which means you have independent prior. But that assumes that you are putting the prior on the model parameter theta. But my aim is not in the estimation of theta. I really don't care what are A0, A1, B0, B1. I may be interested only in estimating the reliability at some mission time. So for example, if an automobile seller sells and gives a warranty that I give coverage for 4 years, they are interested only in knowing what is the reliability at the age of 4 years old in a car. They are not interested in what is A0, A1, B0, B1. So the prior information they will have will not be about A0, A1, B0, B1, but they will have prior information about only the reliability. So in this case, is it appropriate to use the usual Bayesian framework in which you give model parameter specification under prior? So there are 3 types of prior that you can discuss. If my goal is to give a prior on the model parameter vector, which in the previous case was 4-dimensional, I can use a Laplace prior, which will take some form of this type where I have absolute value, and I have a theta g, which is for the gth group, gth parameter, and I have theta gh, which is my prior specification. Or I can put a multivariate normal prior, in which case I can put the prior directly for the reliability function at the model parameter theta. So I have a RIH and I have the prior or tau I theta square, and that will correspond to the model parameter. But notice here that I am giving the prior for the whole parameter theta vector. But sometimes you can give prior just for the reliability function. For example, the automobile dealer will know what percentage of cars had airbag failure before 5-year warranty expired. So in which case they will say we sold 1,830 cars, out of which 32 of them have airbag failure. So that's a prior on f of t. So in this particular case, f is always, f of tau I is always between 0 and 1. So we can give a beta prior, but not for the parameter theta, but we give beta prior for the reliability function itself. So the priors on the top are for the model parameter, but the prior in the bottom is for the reliability function. How do you specify? The results you get can be dramatically different depending on how you set the priors. Here I give you, once again, the same example as before the simulation study. I have an exponential lifetime distribution. I have x naught, which is 2535, is the normal operating conditions for the two stress factors. And I have given the bias and the root mean square error of the Bayesian estimates of the model parameters. Remember how many model parameters I have? Exponential distribution as a scale parameter, only one parameter, but I have two stress factors. So I will have an intercept and two slopes. Those are E0, E1, E2. The true value, we gave E1 and E2 to be the same, and we look at what happens to the bias and root mean square error. And you can notice some dramatic difference. And the prior makes a huge difference. For example, if I used a normal prior or Laplace prior, for the parameter E0, I have a very large bias. You'd see here, I have 1.4 compared to -6. That is something close to 25% bias. The normal case does not get rid of it. That has about 9% or 10% bias, 0.57. But if I had used the beta prior, which uses the prior on the reliability function, my bias of this parameter is considerably smaller. This is what I mentioned. So in a reliability experiment, the Bayesian elicitation, what format you get the prior makes a big difference. And you can also see how the estimates of the mean and the reliability. You can see here the beta prior, which gives prior for the reliability function, results in almost unbiased estimate of the reliability at operating condition of 10. The true value is 0.799. I get here 0.804. That's almost equal. And I also have the standard error to be much smaller than the model prior specification. You can do the same for the other data, glass capacitors data. For gamma and Weibull lifetime distributions, I have three parameters because I will have two stress factors in a glass capacitor's data. So the scale parameter and the shape parameter will have intercept and two slopes, A0, A1, A2, R0, R1, R2. For the gamma distribution and Weibull distribution I have given here, those are the estimates, and I have given different priors, and it turns out that the prior specification makes a huge difference. And that is what I meant to say that the prior specification is important. Now, one of the things that comes across here is immediately you are worried about model misspecification. Because we have no model validation technique, no goodness of it, you can very easily specify the lifetime model to be a wrong one. So the true distribution is A. The data ZA are observed. So you are observing data, Z data, from the true distribution A, but you don't know what the true distribution is. So you misspecify the distribution to be B, in which case my theta that I get for the distribution B is a quasi MLE, because it is not the MLE of the true distribution. So that I denote by theta ABQ, because it is a quasi MLE. I actually minimize the minus log of the likelihood function under the wrongly specified model theta B, even though the data is observed from A. And by the way, this goes back to Kullback-Leibler divergence. This quasi-MLE actually minimizes the Kullback-Leibler distance between the two distributions. There is a whole theory behind it. You can define the relative bias of the estimator of the parameter of interest, phi. You can say, what is the estimate of the parameter phi of the true distribution when I wrongly fitted by the model B, compared to what phi would have been if I used a correct distribution A. And this, you would expect it to be close to 1. That means the model is quite robust. -1 will bring it close to 0. And the coverage probability you can define similarly. You can use, for example, the log likelihood based information criteria. You can use an Akaike information criteria, Bayesian information criteria to choose between the two models. Actually, you can do something more. You can use a specification test statistic, which is not often discussed. People usually talk about AIC and BIC, select the model with the minimum value. But in this particular case, what you can do, you can actually specify a specification test statistic. So for example, if I look at the deviance between AIC G under gamma and AIC Weibel, this is the quantity that I am looking at. And I can do resampling to find the critical value. I can ask, based on the specification test statistic, does the AIC support the gamma against the Weibel? In other words, you want to know whether it is significantly better than Weibel, etc. And the specification test statistic that you use based on BIC or AIC will all turn out to be the same. And there is also another thing that we can do. Those of us who work on multivariate count data, there is something called distance-based test statistic we can do. How do I do that? I assume a specific lifetime distribution. I test NI units, KI units I test, NI units failed. That is the observed number of failure. But if I assume a gamma distribution, once I estimate the model parameter, I can go and estimate F hat tau I. That is my MLE of the failure probability at inspection time tau I. I multiply by KI the number of units that I test. Absolute deviation will tell me whether the deviance is too large or small. If I do that, if the maximum turns out to be too large, that tells me that the distribution that I have assumed is not a valid model for the data. Now, this method has an advantage because you can calculate the exact p-value based on multinomial type argument. If I want the p-value, I ask, what is the probability the maximum of this test statistic exceeds the value m that I got for the present data? But that is a maximum bigger than m. So that tells me that if I take the complement, maximum is less than or equal to m. If the maximum is less than or equal to m, all the deviances should be less than or equal to m. Use the multinomial type argument. You can immediately write the exact p-value. If the p-value is small, the reliability engineers usually use 5% or 10%. You can say that the data do not provide enough evidence towards the assumed model. The advantage of this method, it is exact and it is easily implementable. In our book, we have given the R code for it. And here is what I have given here. Why the model misspecification study is important. You see the relative bias and root mean square error of the mean lifetime and the reliability at mission times. mission time of 10 years, 20 years, 30 years, and 40 years. K is the number of units that I test. Mean lifetime, what is the bias? That is what is produced. So what does this value 0.1613 mean? 0.1613 means that the true model is gamma, but I wrongly fitted a Weibull distribution. I end up estimating the mean lifetime 16% larger. 0.16 is the ratio. So that is 16% larger. And that's what that says. So here it is, for example, I look at the relative bias under the gamma model. Actually, I fit a gamma model. You notice here, the bias that I get is very small, 0.057. So that tells you that you end up making much more serious error. And the same thing holds for the reliability function. So the model misspecification is important. And I give you here the coverage probability of mean lifetime. So what you can do is, before you estimate, you can use the model deviance criteria or distance-based statistic to test whether the assumed model is good or not. If it is suitable, then you go and construct a confidence interval. If you do that, you improve the coverage probability, which is what is mentioned here. So even if I test 50 items, which in reliability context is a large number, you never test 50 items. If I fit a confidence interval for the mean lifetime under the true assumed distribution and under the wrongly assumed distribution, you notice here that I have a lower coverage probability, but I can use the deviance criteria and then fit a confidence interval. The coverage probability gets close to the nominal interval. So that's an important point. And here I give you, for the mice data, the Berlin et al. Study. I have the MLEs for exponential, 2 parameters. Gamma and Weibull will have 4 parameters. Those are the intercept and slope for the scale, intercept and slope for the shape parameter. They cannot be compared because the distributions are different. And I have given here what is a maximized log likelihood value. The maximized log likelihood value under exponential turns out to be minus 294. AIC turns out to be 592. And I have given here the value of exact value of M, which is the maximal deviance, absolute deviance statistic. And I have the exact p-value. Remember that there is no approximation here. It is an exact p-value. This seems to suggest, based on the deviance statistic, that the Weibull is a better fit for this Berlin et al. Data, and that is also supported by the log likelihood, AIC and BIC. And the M value you can calculate, the P value you can calculate exactly. Now, one of the things that the previous study showed is that if I use the wrong model, the estimates can be quite sensitive. So it suggests that we can use a robustness idea here. One of the robustness alternative to likelihood test and likelihood estimate is what is called as WMDP estimators, weighted minimum density power divergence estimators. They have similar properties as the MLEs. You can do asymptotic test like score test, etc. based on this. And what that is that it calculates the weighted power density power divergence between the pi I theta. The pi I theta is what the proportion or the probabilities that you are interested in estimating. The probability of success in I different test condition, and what you have estimated pi hat, you set up a deviance statistic and you give a weight, because the deviance statistic can be swayed by how many units I test. If ki is the number of units, k is the total number of units, I put a weight ki over k. If all the k's are equal, then this will disappear. So the weight is important because you don't want a unit with small number of units tested as group to dominate those which were tested with a larger number of units. And then all you do is you use org min for this power divergence criteria, and you can set up a EM algorithm, which is done in our paper. There is a paper in IEEE Transactions on Reliability on this topic. And you can show that the asymptotic distribution of this robust estimator, weighted, so that's what I say here, weighted minimum density power divergence estimator, can be shown to be asymptotically normal, and it is asymptotically unbiased, and it has a root K consistency, and you can actually use the delta method to come up with a consistent estimate of the variance covariance matrix. And using that, we can develop a Wald type test. The Wald type test, you can do any parameter in a subset. Theta is in theta naught. For example, you can ask, are the scale parameters the same? Are the shape parameters of gamma the same, etc.? Or you can ask, in the gamma family, is exponential reasonable? The shape parameter is 1. So theta naught is some specified vector, and I want to test whether theta is in that subspace or theta is not in the subspace, and you can use Wald type statistic, and you can show it as an asymptotic chi-square distribution. And here I show you what is the significance level and the power of the Wald type test. Of course, the significance level will get closer and closer to 0.05. You can, as the sample size increases, the values get close to the nominal level. When the sample size is smaller, it will have a larger variability because we are using the asymptotic property. And here is the power. You can notice that the power will become significantly higher when K increases. What is the advantage of this method? So here I have taken the Zeeland's data, and I have the exponential lifetime distribution. One thing I forgot to mention, that all these procedures have a tuning parameter. The tuning constant is something that is up to you. It is omega. Omega is like a tuning parameter that we have to use. For example, in non-parametric density estimation, you have omega, smoothing parameter. We have to use the smoothing parameter so we can evaluate at different values of omega. There is a problem with the choice of omega. When the omega is small, it will get close to the maximum likelihood estimation. When the omega becomes large, it will protect you from outlying values or model departure. But we have to strike a balance between the two. If the omega is too small, it will have higher power, but only under the true model. When the omega is large, even if the true model is violated, you will have protection. But if the true model is the model that is correct, it will have a loss of power. So that is what is demonstrated here. The estimates can significantly differ depending on the choice of omega. So we have given a model validation method in our paper in IEEE Transactions on Reliability, where we have given a data-driven method for the particular choice of omega that is suitable for a given data. Now, you can do other things. So far, I have talked about only a lifetime distribution. But remember, the stresses are in increasing order. I have temperature, nominal temperature of 20 degrees, but I test at 25 and 30. So I can think of proportional hazards model, in which case I think of the cumulative hazard function at time inspection time tau I to be some baseline at tau I times nu I, and the nu I links to the covariates. So I have J stress factors. So it will be e to the power summation Hj xij. Hj are the model parameters which are coming from the proportional hazards model. We can immediately turn this cumulative hazard function to the estimate of the survival function or the reliability function, which is nothing but the reliability at time tau I under the proportional hazards model is the reliability at the baseline tau I to the power e to the power this. This is like an accelerated failure time model. And we can estimate, and here I have given how the coverage probabilities and the average width looks like. You see here, there are two parameters, H1 and H2, and I have 30 units tested, 200 units tested, and I have 95% using the logit link function that I mentioned earlier, and the confidence interval seem to maintain nominal confidence level even with a small sample size of 30. So why is the need for larger sample size of 50 or 200? The precision improves. So the average width of the confidence interval with k equal to 30 is 0.076. With k equal to 200, it is 0.029. We can also estimate the reliability at nominal level, and you can see that the reliability estimates are very good. So now I come to the mice tumor toxicology data. The mice tumor toxicology data,
Professor
sorry.
Professor Balakrishnan, if you don't mind, I would like to inform that you have 5 more minutes.
Okay,
around 5
I will
minutes.
finish
Is that
it
okay?
in 5. Yeah, I will
Do you
finish it
think that's
in 5
okay?
minutes. Yeah.
Okay, no problem. Thank you very much.
No problem. And I have taken the exponential distribution here. I have taken the Weibull distribution here, and I used the exact maximum deviance statistic corresponding p-value. It seems to suggest that the Weibull distribution is a reasonable model for this data. The p-value under the proportional hazards model says that the proportional hazards model is not reasonable for this data because the p-value is small. And I can fit in the MLEs and the confidence intervals, etc. And now, since I have run out of time, I am not going to go over the details, but I want to give you a gist of what are all the other issues that have been tackled that you can find in the book. So far, I have talked about inference. I never talked about a design. How to design a one-shot device experiment. If you are going to use mice are expensive, difficult to get. How many mice should I use and when to sacrifice them in order to maximize the information? This is called an optimal design with a budget. For example, you may have a budget of $300,000. And then in the lab experiment, they say that, well, I can do the test for 36 months. The termination time is 36 months or the termination time is 60 months. The budget is 300,000 or 500,000. How many mice I should test under what condition? And that is a question. And you can use an optimal design experiment by minimizing the asymptotic variance. And that is what is done here. And we show how the optimal design can be done, and there is a EM approach for its implementation. And I have shown here that instead of budget based on time, instead somebody says budget is not a problem. I want a precise estimate. My standard deviation at the termination time that I estimate the survival function should be less than or equal to 0.1. In which case, what is the corresponding budget you need? The expected cost of the experiment, and that can be studied. And you can do a sensitivity analysis of optimal design. You notice here the optimal design is going to ask what is the choice of the parameters, and that is a priori fixed. So if I have several parameters, R0, R1, S0, S1 in my gamma one-shot device, I can change the parameter setting. What happens to the optimal design? What is its relative efficiency? The last column says what is the relative efficiency. The frequency says how many observations I should make. You will be surprised to see, even if I misspecify the parameters, the number of observations that I make are all the same. The variance efficiency is very close to 1, 98 or 99%. That says that this EM-based, likelihood-based optimal design construction is quite robust. You can do the same with a simple step stress accelerated live test. What that is if I think of a simple case, there are 2 stages, 2 inspection times, the stress level gets increased from 1 to 2. This is what is a corresponding cumulative hazard function. It is like a piecewise hazard function, you can do the same. You can develop a Fisher information-based confidence intervals. You can talk about optimal design. It is a paper in IEEE Transactions on reliability. Now, I showed you one data where there were competing risks. This is the glaucoma data. Some died with glaucoma, some died due to other causes, some died due to both. In which case, I have number of devices or number of mice died with delta equal to 0, delta equal to 1, delta equal to 2. If both causes were present, only one cause was present, only the other cause was present, I can use a competing risk model. And you can do the same kind of study, Bayesian, non-Bayesian, classical, etc. This is done. Now, you can also introduce what is called as a masked failure mode. You do an autopsy of mice, you don't know what caused the death of the mice, in which case you do not know what is the original cause. If a machine fails, I cannot pinpoint what exactly caused the failure. This is called masking. And you can use the EM algorithm to do the masked cause of failure data. The final point I want to make is there are a lot of people in Brazil in the statistical community who work with a multivariate model and copula-based model, which also can be done here. I have talked about dependent components. For example, in an airbag, you have what is called as an ignition. The other one is called a chemical balance. Ignition is it sparks, and then the chemical actually explodes. I don't know whether any of you have experienced a airbag explosion. It's a chemical explosion. In fact, you get burn marks on your chest like I did. So in this case, the failure can be any one of the two, either the chemical or the ignition, and they are dependent. You can use copulas. For example, I have talked about copula models here. You can use different types of copulas, Gumbel-Huggart copula, and you use typically Kendall-Stahl as a measure of dependence. You can use Frank copula, and you can do the analysis. And I want to complete with one particular data analysis that I want to show. This is the data that I talked about, Berlin et al. This is the case with the disease category A, glaucoma, disease category B, other diseases, but both the diseases. And I have given here the inspection times, 100 days, 200 days, etc. for the mice. What is absence? What is the absence of A and B, absence of A, etc. And there are different models that are indicated, different copulas. Whether you want to use the independence copula, that means the two causes are independent. You want to use the Gumbel-Huggart copula or Frank copula, etc. And you can do model discrimination and model selection. So the final conclusion I want to say is that large sample sizes facilitate precise estimation, and that's not a surprise for statisticians. It is better to use a flexible model rather than a particular model, because the flexible model can direct you which one of the simpler model is better, and that will facilitate accurate estimation using likelihood or Bayesian criteria. In the Bayesian criteria, the prior specification becomes important. But what the statisticians don't pay much attention to is good design. The reliability engineers always care about good design. How many units should I test? If the units are expensive, you can't go to a manufacturer and say, give me 200 units. Maybe that will cost $10 million. So you have to decide beforehand what criteria you should use, what are the constraints based on which you can develop good designs. So there are lots of future directions. If you read the last chapter of the book, there are many, many things that are given. We have handled only optimal design for a simple stress level. How do you decide on optimal design for multiple stress level is something that we do not know. And frailty models, which can accommodate heterogeneity between units, that has not been done. And you can use a sea salt or an S salt. Reliability engineers prefer sometimes a sea salt, sometimes a S salt. From an inferential point of view, which one is better? A comparison and some guidance is important. So thank you very much, and thank you very much for your patience to wait till the end.
Thank you very much, Professor Balakrishnan, for the talk. I will ask if there are any questions. Então, eu pergunto se tem perguntas para o professor Balakrishnan, para os presentes.
Josamar? Yes.
I have a few questions.
Please.
First of all, I'd like to thank you for your nice presentation. It's very interesting subject. You had a very tragic accident to motivate for this problem.
Correct.
And how do you feel about that?
Well, the thing is, the idea didn't come to me until I had the accident. And also, I told my student, if the other girl who had the accident with me, she was driving a Toyota Corolla, if her airbag had deployed, I would have never thought of this issue. And since her airbag failed, I started thinking, how is it that my car airbag succeeded and her car airbag failed? And my wife kept telling me that, oh, don't worry, you had a better car. I said, no, it has to be based on the reliability evaluation. So the reliability evaluation idea came to my mind from there. Then I started looking into the literature with Manho, and then we found some military test of the US Armed Forces had done the data on electro-explosive devices. And those data were sealed. We couldn't get. But one of the Chinese authors had published electro-explosive device data. We used and started looking for other data sets. We came across about 9 or 10 different data sets that are interesting. All these data sets are presented in the book. We have used different methods to analyze all of them.
Oh, it was a very practical motivation.
So the idea came purely from a practical motivation.
Yeah.
Yeah.
I'm very happy you talk about the Bayesian analysis or problem.
Right.
I have one question. Did you use informative priors?
We used informative prior.
How do you get this information?
That's the thing. That's the thing. We did what we did for the informative prior is we did a simulation study. For example, in the simulation study, we know the true parameter. So what we did was we set up a variance factor in the beta prior. So beta has two parameters, A and B. So we want the reliability to be estimated accurately. The reliability is A over A plus B. So we fixed the true value. The variance is also a function of A and B. We made the variance larger to give a diffuse prior. We made the variance smaller to give a more informative prior. We looked at what happens to the estimate of reliability. As you would guess, the informative prior results in better estimation. But in a practical data, like in the mice tumor data, it is very hard to get the prior. So the only thing we could do was the following. To compare with the Bayesian estimate, we took the true value to be the MLE values. So we fixed that as the true parameter for my multivariate normal prior for the model parameter. Then we allowed individual variability to produce diffuse prior or informative prior. We looked at the results.
Oh, that's nice. Did you try no informative prior, like Jeff's prior, for example?
Actually, one of the things that is present is the non-informative prior, diffuse prior.
Yes.
In the reliability case, it will be uniform, 0 to 1.
Oh, yes.
Yeah.
Okay.
So we did the calculation for that. Yes.
Thank you very much.
Thank you.
Hope you are going well.
Thank you.
Thank you very much, Josemar. I've just seen somebody raise a hand. I think Alex Leao if you want
Yeah.
to, want to
Yeah.
ask something. Okay.
Thank you very much for your presentation, Professor Bala.
Thank
It's
you.
very, I liked you very much. I would like to see your model in the contest freight model. Is this possible?
Actually, that is an ongoing work. One of the things that we did is right now we have captured the variability inherently present in the units, and we have assumed them to be the same from unit to unit. So what we have done is we have developed some results, EM approach using marginal likelihood method, where we have assumed unit to unit variability being captured by a frailty model, and estimation of the frailty parameters becomes quite difficult in the marginal likelihood, because we have to estimate that, and that depends on what your sample size is, how many units we tested. In fact, we have just completed a paper on that. We started with a gamma frailty model, because in the gamma frailty model, the Laplace transform is easy to work out, from which we can calculate all the conditional expectations that we need for the implementation of the EM algorithm. It is a recently completed paper with one of my PhD students, Chenji Yu, and this has been submitted for publication to the high impact journal called Reliability Engineering and System Safety, and where we have done based on gamma frailty model. Of course, that raises you brought an important question. That raises an important question as to how do I know whether the gamma frailty model is appropriate? So in the past, I have done some work in statistics in medicine with the survival data, where I come up with a more general frailty model called a generalized gamma frailty model, which includes exponential, gamma, Weibull, and log normal. Then you can do model discrimination between the frailty models. And that is what this PhD student is going to do next. That's an intended project, but she has finished the gamma frailty model work. And development of EM algorithm, asymptotic confidence intervals, hypothesis testing, etc. We have done all that there.
I understand. Thank you, Professor Bala.
Thank you very much for your question, Alex.
Se tiver alguém que se sente mais confortável de perguntar em português, não tem problema, eu posso ajudar com a tradução, né? If anybody wants.
That's a good point. If somebody wants to ask the question in Portuguese, it's okay.
I have a question, but it can be English. I would like to know if in your book, do you have the steps to sample from this kind of data? I'm having some hard time trying to simulate the synthetic data using one-shot devices. Where can I find a good reference to do the simulation?
Oh, that is, the R code is actually given in our book. We even gave a specification of how to simulate how to simulate one-shot device data, and there is a simulation study, and the R code is given in the book itself. You can see in one page it's highlighted as an R code. It's a specification. What distribution you specify would determine how you want to do the simulation. What you have to do is fix what reliability you want at specific times, right? And there is not a unique choice for that. So what you do is you have to use trial and error to, if I want a 90% reliability at a mission time 10, R10 should be 0.9. But under gamma and Weibull, with the different stress factors, there are many choices. So it tells you how to go about doing it. If I now take it from there, I want the reliability at mission time 20 to be 0.7, it puts more constraints how to go about doing the simulation.
Ah, great. Thank you, Professor. I'll take a look. Thank you very
Yeah.
much.
Okay, good luck.
I'm just trying to look if there if there are other people that want to ask questions. I don't see if anybody raised a hand. Eu estou tentando ver para saber se tem outras pessoas que perguntaram ou levantaram a mão, porque aqui no celular não consigo identificar onde tem que apertar para saber quem levantou a mão. Tem mais alguém que gostaria de perguntar algo em inglês ou em português? Is there somebody else? In this case, my question is a bit more general. So I see that it started with a relative dramatic event, this research, and I hope you said the other person, the young lady, was seriously injured, and I hope she recovered. Yeah.
Yes,
later.
actually, we keep in touch because she was of my daughter's age. We went to the hospital. I felt sorry for her because she was of my daughter's age. When she was in the hospital, the police came and charged her. They put a fine on her and they gave her 3 demerit points. I was telling the police officer, you know, she is young. You can excuse her. It's okay. And he said, no, a law is a law. And so she got charged. And I visited her in the hospital because she stayed in the hospital for 2 weeks because she had a back injury because of airbag not deploying. Yeah.
But I hope she could later
She
recovered.
She recovered well. Yes. Yes.
That's good. So in the end, it seems everybody recovered that became really injured. But I'm just curious, did this lead to some kind of project or work together with auto manufacturers or airbag manufacturers? Did it lead to some close cooperation on some projects until this point?
Actually, one of my students has just joined General Motors last year, and he is in Detroit. And he is actually using some of these. You know that in General Motors, they produce data. In fact, what they do is they have deliberate collision so that they put a stationary object and they accelerate at different speeds, and then they evaluate. The data is not only for airbags. The same data is also used for the strength of the bumper in the front, the bumper in the back, how strong is it, how much of a dent occurs, etc. So they do that, the body collision evaluation as well as airbag. He is trying to implement some of the technology that we have developed into the GM package. But the data, these collision data from GM, you cannot get them out. They don't release the information at all. And so the only thing is, I know somebody by name Betty, and she told me that there are data available, but they are confidential. We cannot release. But fortunately, my student has just joined their R&D and he is using it. And he even told me that Henry told me that even if he writes a paper in the future, they have to fudge the data because they cannot display the real data. They have to change the data so that you cannot infer from it the true data. Data confidentiality. Yeah.
I understand. But I see that there is there are probably come to life some projects of some work or more closely if your ex-student he joined General Motors. I was born and grew up in Germany, and there the ADAC, which is a automobile club, they usually crash test every new car in Germany.
Correct.
So they crash cars all the time to test, and they put how do you call it? I forgot. Just like of some kind of material, the person in there, and then they evaluate what the damage has been to the car, the person in there, you know. And so,
by the way, there is one data which I didn't show. That's nothing to do with one-shot device, but there is something called test on dummies, and and they put a helmet. So this is a famous data, helmet crushing data, and they have a dummy, and the dummy is shot at various speeds, various accelerations. How much of a damage occurs to the helmet? They evaluate, and that data is available publicly, and it's a famous data. It's called the helmet fracture data, but that's not typically one-shot device, because you can actually evaluate how much of a damage occurred. It's not just 0 or 1. Helmet can be dented slightly, no dent at all, fractured like it broke into 2 halves, etc. You may get more information on it.
I understand. Yeah. Of course. Okay. If there are no more questions, I haven't seen anybody raise their hand. Yeah. If somebody, if I'm leaving somebody out, please tell me. In this case, I thank again Professor Balakrishnan for the presentation today. It was a pleasure. Thank you very much, and I'll give the word back to Jeremias.
Thank you.
Thank you, Alex. Thank you, Professor Bala, for the talk, and the graduation program of mathematics of da Universidade Federal do Amazonas are grateful to accept the invitation to present this lecture, and it's a pleasure for me participate of your lecture, as well as see friends like Professor Vera, Professor Josimar, Pedro, and the others, and I hope we can participate in Congress in person soon. I remember in 2019, we participated of the WASA in Piracicaba. It's a pleasure to see you there.
Yes.
Thank you again,
It was
Professor.
a nice visit to Piracicaba. I still remember.
Thank you again.
Thank you very much. Thank you very much for the invitation. And I hope the talk was of interest to some people. And if anybody goes through it and they have questions, they want to work on it, any problems, please feel free to write to me. I'll be happy to correspond. So my email is very simple, bala@mcmaster.ca, and it will be a pleasure. Thank you very much.
Thank you, Bala.
Professor.
Thank you.
Bye-bye.
Thank you very much.
Bye-bye, Bala. Thank you.
Thank you.
Thank you.
Thank
Thank
you.
you.
See you next week.
See you next time. Bye.
Bye.
Bye.